Good evening, and welcome to Louisville Late Night. This evening we're in beautiful Jackson Hole, Wyoming, and we have a special event going on. It's the birthday of C. Fred Moore, who is a nuclear physicist from the University of Texas in Austin. And Fred has been experimenting with these nuclear entities for many years, and he grew up in Louisville, Kentucky, and went to St. X High School. He got a master's degree at the University of Louisville, got his Ph.D. in nuclear physics at the Florida State University in Tallahassee, and then he became a professor at the University of Texas in Austin. He's done research in a number of nuclear facilities throughout the world, and he's done many different things. I don't know what all we'll get into this evening, but first of all, let me say happy birthday and hello to C. Fred Moore.
Well, thank you.
Fred, you were speaking a few minutes ago about Galileo and the development of the notion of
the Earth going around the Sun, or the
right.
Sun going around the Earth.
Right.
Galileo being put in house arrest, just like what's her name, Stewart, the lady who's
Martha Stewart.
Martha Stewart. She's under house arrest now too.
Yeah.
Or something probably very similar to the Galileo Pope incident.
Really? Well, what happened with Galileo?
Well, Galileo stole this idea about how to make telescopes. And he looked up in the sky and he saw that Jupiter had moons going around it, and that it made a lot more sense to him to think that the Earth was going around the Sun rather than the Sun going around the Earth. Now the Sun goes around the Earth from a biblical point of view, because in the Bible it says that the sun rises. So therefore you think the Earth is stationary and the sun goes around the Earth. Well, Galileo thought that the Earth went around the sun. So there was a big controversy, and they had a...
And Galileo came to that conclusion because of observing the
planetary system.
And the moons of Jupiter or something?
Yes, that's what he first saw. But the Earth couldn't be the center if there were things that were around Jupiter, because it made Jupiter, the center of something. Its own moon system. So Galileo went to jail. Well,
he went to jail for saying that the Earth wasn't the center.
Wasn't the center of the universe.
Okay.
Now, in more recent years, you don't worry about those kind of things because, Einstein and modern thought is that everything is relative. But this is a particularly important aspect of what's relevant. I mean, from a point of view of logic, you don't say that the sun goes around the Earth and the Earth doesn't go around the sun. If the sun goes around the Earth, obviously the Earth goes around the sun. It would be stupid to say one thing goes around something and this other thing doesn't go around it's a matter of where your coordinate system is set. So let's just draw a picture here.
Okay.
Here's the sun, and here's the Earth going around the sun. That's Earth, and it goes around. So that's a pretty poor picture. I mean, you'd have Mars going around down here. Not a very good picture. But so Tycho Brahe, a famous astronomer, came up with the idea that all you'd have to do is make a transformation of a coordinate system, and you can put the Earth at the center and let the sun go around the Earth. And if you did that, then you would have a picture of the Earth here, and you would have the sun going around the Earth. That's the sun. So then you say, what about the other planets? So let's take the planet Venus. So Venus would go around something like this. And this was Tycho Brahe's picture. This would be an ellipse where the sun goes around the Earth. And these are an epicycloid. Now you sit there and think, why is that important? Well, that's important because you want to be able to go out at, say, 1 o'clock in the morning, set your telescope up, and point it towards all the planets and see if the planets are lined up. If the planets are lined up, then the king could, get together with his wife and produce a baby, and it would be a boy.
Oh, really?
That's the way astrology works.
This is medieval thinking, eh?
How do physicists get their money?
How?
They get their money from the government for solving, you do plasma physics in order to cure cancer, right?
Okay.
You get money from the government. That's a little far-fetched.
But back in the medieval times, the physicists
you
were...
had to line up the planets, and then you can start a war and win a war, or you can have a male child, or whatever you wanted, and that's how astronomers and physicists got funded. Lots of money involved. So, Tycho Brahe had this picture where the Earth was the center, and the sun, the different planets went around the sun in epicycloids. Let me just say what a cycloid is. The cycloid, if you take a circle and you roll it on a flat plane, then the cycloid would be a point on that circle as it rolls around, as the circle rolls down the plane. And an epicycloid is a circle rolling around on a circle. Okay, so here I am growing up with Patrick in Louisville, Kentucky, in a state known for beautiful horses and fast women, right?
Right.
And I'm kind of feeling a little bit out of whack because I was in the zoom, zoom, zoom. This is, 200 years ago when I was young. And there was this place up in Indianapolis where they had these races with motor cars. And the race would start out when Bernie Oldfield, and they would go around the racetrack and then about 100 miles, and then the car would stop because the gearbox blurred up.
Right.
So that was terrible. So what do you do about this? Back in those days, they would make gears, and actually, we can draw another picture here. You'd have one gear and another gear, and a tooth here, a cog here, and a cog here. And when the cogs, got together, they rubbed against each other. And that when they rubbed against each other, it would wear out the gears, and the gears would get hot. So the gearboxes burned up. So back, in the 1920s or somewhere thereabout, they went back and they looked at what Tycho Brahe had done with these epicycloids, and they said, if you take the gears, the teeth on the gears and shape them in the shape of an epicycloid, then let's just draw two surfaces together. Then the forces would be normal, and the gears wouldn't shift on each other. So you wouldn't get hot gears. That's what's called a planetary gear system.
Did they literally call it that?
Oh, yes. You don't know what a planetary gear system is? They used to advertise Louisville had planetary gears.
No kidding.
That was a great thing, when these new gearboxes came out. Anyway,
all right.
That all comes from the fact that the Pope and Galileo had arguments. You wouldn't have all this mathematics and nice methods of making gears if you didn't know how to draw all these different curves. in order to make things work without any systems. I teach physics, and you know, if you're teaching introductory physics, it's very interesting to tell students, you know, how things interact and they become important. Even if at the time people were arguing about whether the Earth went around the Sun or the Sun went around the Earth, you know, a stupid question, because they both go around each other. And how it comes down to where it's very practical in the end. In fact, one of the things I worked on way back when I was a student was we got a germanium chip from AT&T and went and put it in an accelerator experiment, and we were able to detect incoming particles just by a little pulse that they made in this chip. The chip didn't work very well. The conclusion of the experiment was that solid-state devices were so impractical because they broke down all the time. And you could, you know, they would spark, and you couldn't rely on them. That solid-state devices would never be used. They were just a good toy. Even though we were probably the first person to ever use a solid-state device in a practical sense. It was practical in the fact that we made it work, and we were able to count, you know, charged particles going through this little germanium chip, but it was not as, it was harder to do than doing it with some kind of crystal and a photomultiplier tube. But it did work.
Where did your research go from there? I'm just curious. I've never really had much of an understanding of the. I know that a lot of your life has been that of a teacher, but a much greater part of your life has been that of a researcher. What kind of research have you been involved in? Could you describe it?
Well, the important thing at that time of my life was the discovery of isobaric analog states. I mean,
and that's what you did over in Germany, right?
No, that's mainly what I did that in Germany, but that was, the discovery was made at Florida State University. And basically there you think of we normally think of nuclei as being made up of neutrons and protons. Okay. And neutrons and protons have spin. But you can also think that a neutron and proton is the same particle, and it's either a proton or a neutron, and that's called isospin. So if you just look at things like giant resonances, you would say, here's the protons, and here's the neutrons, and it's all one big soup, and the neutrons and protons are vibrating against each other, and you get some kind of a giant resonance. You can also think about single particle states, where you have a proton going around the outside of a nucleus, and you have a neutron going around the outside of a nucleus, so you have some particular state. Because one of them is a proton and one's a neutron, it's going to be in a different nuclei, but it's the same nuclear state. Okay. And that's what we basically found. All these states and other nuclei that are built and identical to states in what we call the parent nuclei. So we're able to classify hundreds of states and nuclei and make good sense out of it all. And you can look at how some of them decay and figure out what the nuclear structure of those states are.
So is that what you were doing at the Max Planck Institute?
And we were doing further studies of isobaric analog states in Germany.
And what have you been doing more recently, research-wise?
Well, I went to Los Alamos, and we were doing meson physics, where we were scattering pions off of nuclei. And that's pretty exciting. We saw all kinds of different states in nuclei that are excited by pi plus and pi minus mesons, exciting nuclear structure. And You know, what's exciting about in physics are things that are simple.
Oh, really?
And most of the things that we did at nuclei at Los Alamos are not all that simple, like
really?
isobaric analog states are. And so it makes it a little bit complex to explain this to you. Let me go to a different aspect of things. So while I was in Los Alamos, one of the ideas that we had was taking, there's a nuclear test ban treaty, and we have to get rid of a lot of our nuclear weapons. Uh-huh. So how do you, if you have, I don't know, 20,000 nuclear weapons, and your treaty only allows you to have 600 of them, then hopefully you want to throw away a whole bunch of them. So how do you decide which ones to throw away? Well, just like you take people like Patrick, who's a psychiatrist, and you want to find out whether they have good heads or not, you go do a CAT scan on their head, and you see if their brain is working okay. Well, you can't really do a CAT scan on a nuclear bomb because there's so much metal in there that the X-rays don't penetrate. But you can do a CAT scan, instead of using X-rays, you can do it with a high-energy proton beam. So we did CAT scans. Well, since I'm at a university, you don't have much of a clearance. So we developed a technique for doing CAT scans on nuclear weapons. And I assume that they are doing that in order to decide which nuclear devices to throw away and which ones are to be kept. But the same technique can even be used in a much more interesting way. Uh-huh. For example, you can take a gasoline engine in a Ford automobile car and do the same instantaneous CAT scan, and you get about 6 pictures of the inside of a cylinder as the spark plug sparks and the explosion pushes down the cylinder. And you can see if that explosion is uniform, if the pressure wave is hitting the top of the cylinder, and if you get the maximum amount of energy out of this engine by the way you design the cylinder and the spark plug and the top of the cylinder. So it has a tremendous amounts of applications, even if you're not very interested in the weapons development.
Weapons. What about this thing? I mean, weren't you doing something where you were smashing things into each other, nuclear?
The present research that we're working on is what's called relativistic heavy ion physics.
Relativistic?
Relativistic, yes. You see, nuclei.
Okay.
Nuclei are basically spheres.
All right.
Okay, and then special relativity, you can say if something's going almost at the speed of light in that direction, then it gets shortened. That's called length contraction.
Okay.
So now if you take a sphere, like a nucleus,
okay,
and you make it travel almost at the speed of light, it goes along, and as it becomes a pancake. So you have an accelerator that's circular, or almost circular, and you send a beam into it, and it goes around one way, and you send a beam in it, and it goes around the other way, and you focus the two beams together here, and they collide. So what does that mean? That means that you're taking 2 of these pancakes that are going at 99.4% the speed of light, and they collide with one another. They have so much energy. Now these are nuclei. If you were traveling with the nucleus, you would see a sphere. In the lab system, you see a pancake. Those 2 pancakes go together. They have so much energy, they go right through each other.
Wow.
So now you have something that has a much higher density than nuclear density. You have something nobody on Earth has ever seen before. This has relevance to thinking about the Big Bang theory, about the creation of not the creation, but the beginning of our universe. Because the idea there is that all the matter was in one place, it was tremendously dense, and it expanded out, and all these planets and solar systems, etc., has been created from the Big Bang. The Big Bang was something much more dense than anything we see on Earth. So by making this system that's much more dense than anything we've ever seen on Earth before, we expect to learn something about the early universe, and we expect to learn something about the quark-gluon model.
The quark?
Quark. Okay. You know, there's four quarks in a gallon.
Okay.
Our ducks go quark, quark, quark. well, physicists think that there are 3 quarks in a proton.
Okay.
And 3 quarks in a nuclei. These are different kinds of quarks. You can't get them from your milkman.
Okay. Is this what you've been doing up in Brookhaven?
That's right. Yes.
Up in New York.
Yes.
And how's it been going? Have you discovered the Big Bang?
Actually, this is a little bit strange. We have, let's say you're scattering gold on gold. Gold has 197 nucleons in it, protons and neutrons. So you basically have something with about 400 particles each when they collide. Now, at the moment that it's just like the beginning of the universe. At the moment they collide, you have this high density matter. And so that gives you the possibility of creating many, many, many particles. So we have 50,000 particles come out, or 5,000 particles come out of this one collision. So you want to know what's going on in that collision. Well, in order to figure out what's going on in that collision, what you have to do is you have to track every one of these particles, determine what it is, whether it's a pion or a kaon or some strange particle, strange being a quantum number, or whatever, and then you have to trace it back to see if you can make some sense of what caused it. And the main thing that you see are jets, where a whole bunch of particles fly out in one direction, and usually some particles fly out in exactly the opposite direction, but it's a preferred direction. And you try to correlate this with some kind of aspect of the quark-gluon model and the collision process. And this, in general, you can make some kind of ideas about how this works, but we have really not made much progress on understanding the fundamental properties of the quark-gluon plasma. See, the quark-gluon plasma is where choral symmetry is again conserved. It's like going from ice to water and water to steam. You make a change of state. Now, when you go to the quark-gluon plasma, you have more degrees of freedom, so it's a completely different state of matter. So you want to study that state of matter to see what's going on and to try to understand, our state, just understand nature in general. And these are the first experiments to try to do that.
Wow.
But I make fun of it.
Oh, really? So
yes, because what do you have? It's just like if you're a farmer and you go out into the field and you pick up a cow pie, and you pick up 2 cow pies and you throw them at each other, and they hit, and just, I don't like to use this word, but shit flies everywhere. And what we're doing is we're looking at every little teeny speck of this stuff and trying to go back and figure out what's going on. And that's overwhelming. The amount of data that we take, if you put them on CDC, on DVD discs without the covers on them, just collect the data and stack these discs on top of each other. Last year, we took enough data to fill up DVD discs And when stack them on top of each other, they would go from here to the moon and then halfway again.
Wow.
There's so much data we can't possibly use it. I mean,
Wow.
we just don't have the facility for using that much data.
Well,
So we have these meetings and try to decide what data to keep and what data to throw away, and they're political. You know, I want to keep a certain amount of data for one experiment, you know, one idea. Somebody else wants something else. And it's, you know, it's interesting. You have these political arguments about science.
I guess only physicists like yourself can really understand what you're even talking about. Fred, we have to close this show out, but I want to ask you if you want to continue with one more show and go a little bit more into some other interesting aspects of your life. So thank you very much, and we're going to take a little break.